Hello everyone, let's talk about Neopixels and how to control them. Neopixels are very neat LEDs. They are full color, and if you search on Google and if you buy various interfaces, they are sold as strips where you can control every single LED with its color and brightness and all that, but they also come in different shapes. Like this is a circle, there are matrices, you can display text, you can display emojis, so generally quite neat devices. Now, if you want to control them, you have to understand how they're connected. And if you find a data sheet, their actual name is WS2821B. This is the interface that they use. And every LED is actually composed out of 3 different colors, red, green, and blue. And they have a special chip that controls them. And the way you connect them to power, obviously. So there you'll have a voltage plus and ground. And after that, there will be a single data pin that will set the color of the LED. So in order to control these LEDs, in theory, you just connect them to power, and then your microcontroller will send data and you say, set this color and set that color and so on, and they will change very nicely. In terms of protocol, because there's only a single cable, the LEDs are connected to each other. So actually, the second LED is connected to the first, and the third to the second, and so on and so forth. And when you send the data, you will send colors for each of them. So you'll send several colors. In this case, you will send 3 different colors as an example. And what the microcontroller inside the LEDs will do, it will pick up the first color that you send, let's say first 24 bits of color. It will set its own color to that value and forward all the other values to the next LEDs. So D2 will pick up the second color and will start forwarding the third, and it will keep on going until you refresh all the LEDs. And the format, when you look at it, is that the 24 bits of data of colors that are being interpreted are the values of the green intensity, the red intensity, and the blue intensity. And the way you send them is that you have to send either a 0 or a 1 for every one of these bits. And it kind of works like Morse code. So this means when you start sending a high value, it's you tell the LED that, hey, I'm going to send you a color value or a bit value. And then if you send a short high and a long low, it will say I'm sending you a 0. And if you send a long 1 and a short low, then it will say I'm sending you a 1. So in this case, when you think about controlling it, you would think, how about if I change my pin very fast and I just toggle the colors? And here is where the problem starts. When you look at the timings of what these T1 are set, you can see that if you want to send a 0, you have to put 0.4 microseconds high and 0.85 low. And there's a little bit of wiggle room, which is great because otherwise we would have really pain controlling them in general. And then if you want to send a 1, you have to put, like, again, under 1 microsecond on and 0.45 microseconds off. So generally, if you compute this one, it goes a little bit higher than 1 megahertz. So probably it's about 2 megahertz or 2.5 megahertz that you need in order to be able to do these timings. So if you try to implement some sort of loop or some sort of a timer, and you set that timer on a microcontroller at 2 megahertz or more, very likely you will not have a good time, because just the operation of toggling a pin and setting it to high or setting it to low usually will take 1 microsecond or more, and at that point all your timing will be off. So at this point you are trying to probably get around this. So there are a few ways. One idea would be, how about if I write everything in assembly language, because then I have full control about what my microcontroller runs. And this is doable, but it varies by hardware, obviously, so it's not very portable, and it's probably not very accurate. And the other one is to try to misuse or overuse other interfaces. And one of the really popular interfaces that can be used is the SPI. SPI is the serial peripheral protocol, I think. So basically it interconnects 2 devices, and the way they work is you have a clock, and the clock says I'm sending data or I'm receiving data, and then you have a line that says master to slave, which means your device is sending data to a remote device, and then you have the inverse of it, where the device can send data to you. And good thing about this one is that the clock can be reasonably high. So I can set this clock to 2 to 3 megahertz just fine, and it will run. And then when I'm pretending that the data is zeros and ones and I'm sending it with a specific frequency, I can actually control how much it goes up and how much it goes down. So now if I do a cargo search, for WS2812, I will find different implementations. So one of them would be remote, which is specific to ESP32. It's also a way to control signal. You'll see NOP and SAMD. So this is a bit banger. This is the assembly implementation that is not very portable. And then you can also see quite a few SPI drivers. This is one that is that I tried first, and it is based on SPI, and it doesn't require STD. And then there are others that work with Raspberry Pi. So if I look at their description, you will see that this is for Raspberry Pi, let's say 2040. So in the end, what I would like to do in this video is have an implementation of RGB LEDs that are controllable from my Cortex M0. And I start this thinking that I will just import this crate and I will use it and it will be easy and it's done. It turns out it's not that easy, and I will show you why. So if I clone the examples, repo clone smart LEDs examples, and I go into F1 examples, I can cargo build and it will compile reasonably fast, and you can actually probably write this example and everything will be fine. So at least this project is up to date. However, if I will go into the F0, let me find the F0 example. This is the one. It doesn't matter which one I choose. Let's say SPI Blink as well. It will actually not compile. And it turns out the reason for this is that the interface being used for SPI has evolved over time, or something has changed. I see a HAL difference. So what the HAL in the F1 implements is this full duplex interface, which basically says that you can really control when you write and when you read. Whereas the F0 in HAL only implements a blocking interface that says write. It doesn't have this full duplex, and you kind of fail to compile. So at this point, I started with my journey to how about we implement the protocol from scratch, and I will go through that in this video. So let's get started. The way I started is I imported my starter project that does nothing except a LED blink, and I'll go through the steps of how do I implement a Neopixel driver and how do I use it, and maybe we'll have some pretty lights showing at the end of this video. Let's start with a bit of a plan of how we will implement this driver. The driver will be implemented using SPI, and what I will do is, in order for me to simulate LEDs up and down, at first I thought I would use 3 bits. So let's say if I have a signal that takes 0.4 microseconds, maybe when I do the first and I will say low, I want to send a 0, I will put it high for 0.4 microseconds, and I will put it low for 0.8 microseconds. And if you look at the protocol specification, this is reasonable. Like it will be 0.4 and then 0.8 and 0.85, but there is a plus minus, and these devices are not that sensitive. So I would be in range. And the other idea would be like if I have a clock that is 0.5 for microseconds, then if I want to send a 1, I'll put it high for 0.8 microseconds and I'll put it low for 0.4 microseconds. That's great. So this means when over SPI, if I want to send high, or a 1, what I want to actually send is 110, and if I want to send a low, so 0, I'll say 100. And this in theory does sound great, and actually had an implementation of this, and it turns out it doesn't work. And after much digging, I found out why. The reason it doesn't work is that there is a, I guess, undocumented feature or side effect of using SPI on the Cortex M0, and this is what happens if you send a series of bytes and there are interruptions. So my microcontroller will not be able to feed the data line as fast. So it needs to do some computation. So this means I will send something to the SPI, a series of zeros and ones, and at some point there will be a gap. So if I go into my sending and let's say I want to send 1 byte of data and I send 11000011. And at this point, I have to compute what the next data has to be. And I figure out, well, I will make it up, but let's say 10010010. Doesn't really matter. The trick being, in this interval, my data line will do something. It will be either high or low. And according to what this other person found is that whatever was here in one of the high bits will be this state. So this state could be 1111 always, like always high, or it could be always low. And the problem with always high is that if I look at the description of the protocol, the description says, if I'm sending you a high value that is long, please consider the bit as being set to high. So this means if I use this protocol that uses 3 bits, I don't have much control over when I send zeros and when I send ones, because my bytes are not multiple of 3s easily. And from time to time, I will get one of the colors in the LEDs set to high, and one of the LEDs will turn super bright for no apparent reason. And that's extremely annoying, and it took me a while to debug. So I will go back into this, and even though in theory it sounds like this idea of splitting into 3 bytes is good, it doesn't work. So let's split it into 4 bytes. And not only that, we'll split into 4 bytes, and we'll also make sure that always the first byte will be a 0. So I propose this one. When I want to send a high, I will send 011, which since I know that every future byte will start with a 0, this means that in practice I send a high that is 3 steps, and then it will be followed by a low, which will be at least 1 step. And then when I send a low, I will send a 1, which will basically be a high value for 1 step, and the low value, which is guaranteed to be at least 3 steps, because I've sent these 2, and then the other byte will be low. So I will send low 3 plus steps, and here low is guaranteed for 1 step. And in this case, everything will split out nicely, and also I will not have this problem that I cannot control what happens in between bytes. Let's start. So I will be using SPI, as I said, and then I will want to get constants. So if I have a value x for a color, I would like to convert it and expand it into these either 0, 1, 0, 0 or 0, 1, 1, 1. Either one of these two, but this will mean that I will basically quadruple the value. So for every byte value x, 8 bits, I will create actually 4 bytes. So I will inflate the data quite a bit. So my plan right now is to have some sort of a map that goes from 8-bit value into an array of U8 that is of length 4. And then when I actually implement the write, I will instead, whenever I need to write this value into the SPI, I will find the mapping and I will display that one. All this mapping, when I was implementing things, I found it much easier to use macros. I can copy and paste, but in general, like whenever I was doing 3 maps or 4 maps and so on, macros are a lot easier. So I will show you how to build macros and how to compile separate libraries into your programs. So I will start with that. So in this case, I'll do cargo new, and I will call it SPI constant, which apparently already exists. I will remove it because I probably added there just for demo. So cargo new, and this is a clean library right now that has a source that has just tests. I will not implement tests right now. That's fine. And it has a cargo toml, which is quite empty as well. Let me go through updates and we will see how to make this work. So first, cargo toml. I know I want to create some sort of macros. So inside the dependencies, I will use procedural macros because I'll repeat things 256 times, and that will be quite painful if I want to do it manually. And there are other 2 libraries that are useful. One is syn, which its purpose is whenever you pass in something to the procedural macro, it wants to parse it, and parsing Rust abstract syntax trees is kind of painful, so I'm using syn to help me. And then there is quote, which does the inverse. So it generates data once it generates code in the readable manner. And because I'm using procedural macros, I have to tell Rust that my library actually enables procedural macros. And that should be it. Now we can start implementing the library. I will go and generally copy and paste options to explain. So first of all, there will be a lot of use and a lot of includes, which are probably not that interesting, but now individual functions and macros will be interesting. So the first part will be, let's see about converting to bits. So this means when I have individual bit, I have to convert it to 3 actual bits as we discussed. So either a high value, which is 0, 1, 1, 1, or a low value, which is 0, 1, 0, 0. So it does, I put in there a comment explaining why this pattern and why I don't use 3 bytes. If I would be using 3 bytes, here I would return something like 0B110, and here I will return something like 0B100. However, this doesn't work, so I won't do it in this example. That was not easy to find. So for every bit, I have a value that says this is what it expands to. So the next part would be if I have 4 bits, how about I expand them all at once? So I call this nibble 12 to U32. So this means it will encode 12 bits into a 32-bit value. So this means I'll get the highest bit, then the second highest bit, then the third, and then the fourth. So out of 4 bits of value, generate 12. Notice how each time I multiply things by 4. Actually, I don't think it's 12. This is when I was using 3. So I generate 13, 16. Okay, updated. So I generate 16 bits of value. So this is 4 times 4 bits. And the next part will be to implement a macro. Implementing a macro looks kind of like this. A procedural macro is a function, and that function receives Rust syntax and is supposed to output Rust syntax as well. And if you don't want to do any changes, I could just return input, and this is a no-op, so it will not do anything. Realistically, right now I want to convert them, and the way I want to convert them is I would like to generate 256 values for all the possible combinations of constants. So I'll go in here and create a vector because I'm lazy and want to just push data. And then for every value from 0 to 0xff, so for every unsigned int 8 values, I will, with the endings included, I will compute the actual data that I want to push onto SPI. And then I will split that data into 4 different components. Now that I have this data, I will want to convert it into Rust syntax. So this is where I use quote, and I say my actual values that I will want to return from the macros will be, if I look at these 4 values that I wrote into the vector, I will create them as Rust syntax. So in practice, this means that if my values were, let's say, 1, 2, and 3, and 4, this will generate exactly that. It will return 1, 2, 3, and 4. I'm not sure if this is actually required. It's my first time writing procedural macros, but it seems to work, so I kept at it. And then the final step would be, I have all the values. Let me generate my actual macros. And my actual macro looks like this. This is everything is Rust syntax, but with special markers whenever you see this pound sign. So I will generate a constant. The constant name will be the identifier, which I expect it to be passed in the input of the macro. So if the input I say, this is identifier, please parse my identifier. So return value is a constant. I know it will have 256 values in an array, and every value is actually the 4 bytes that I have to write to SPI in order to get that value. And then I tell quote that I want to repeat all these values. This is what the star means, and I repeat them comma separated. So this is my procedural macro, which will generate 256 values, and it will be quite big. We can take a look later on how it looks like. Now that it's saved, I can go into my example code, and I do not need LEDs toggle. I'll do fix me implement, and let's see how to implement some sort of LED writing. The first part that I have is that I already have defined the macro for SPI constants. So I will use it and I will name it in some strange way. Let's say write 3-byte constants, and we'll see if this is compile. It doesn't compile right now because I need to add dependency into cargo, because this is a subdirectory that I just created and cargo doesn't know that I am using it. The way to define this, I use a path. So I will paste something like this, and I will say inside the folder named SPI constants, there is this crate that you can use, and the crate is named SPI constants as well. So now let's save, and it will compile. Great, so now I have a constant. I wonder if macro expand. So expand macro recursively. This doesn't work, but I can show you in the main window maybe. Cargo expand less. I had a typo during copy and paste because I realized that this is not 12 bytes and it's 16. So let's correct that. Let's see if cargo expand works now. So you can see what it actually generates. When I go into my main rs, this is what I write, but the actual code that it generates is what my quote wrote. So it will say const, it will be the constant that I wrote, it will be the text that I wrote in my macro, it will be this 256, and there will be every single value separated by comma. And you can see why I didn't want to type this thing manually. It also makes compilation slower, so there are some trade-offs. You cannot use macros everywhere, but in this case I think it's reasonable enough. Let's keep going. I'm switching for editing speed. I'm actually switching back and forth between code so I can copy and paste code rather than me typing it and being slow at it. So the first thing to do is I know that if I have some SPI driver, I will be able to generate an LED writer. And the crates that I imported actually define an interface that's called smart LEDs, right? That looks like this. And it says that if you implement a function named write, you can write LED values. And the smart LED library has things like RGB8 and so on. So speaking of this, because I was copying and pasting, we should add the dependencies for the smart LED libraries. I will add all these, probably in the wrong location, but that's okay. Typos. Okay, so these are the new libraries that I just added. This is my local constant macros below. And I will go through them why I added them. So once I have this SPI driver, this actually doesn't work, so I can actually remove it. I used to test it and it works for an F1, but it doesn't work for an F0. I am adding the embedded HAL because this has some declarations of how I can write to SPI. I'm adding the smart LEDs, which defines the interfaces of how you write to LEDs and defines the structures that are quite nice, like RGB8. It means it's a red, green, blue structure. Anyhow, I enable because I want simple errors and I don't want to bother what error types are, and I just want to return anyhow error, and that's it. And I will use some dynamic memory allocation. I'm actually not sure why this is needed, but it won't compile without. So I believe one of the smart LEDs probably, or anyhow, one of these two libraries requires memory allocation. So I will need to implement it. So let's go back here. So I need to implement a smart LED write, and I will use RGB8 values. The trick with Rust traits in general is that you are only allowed to implement a trait either if your crate defines the trait or if your crate defines the type. And the reason for this is that it doesn't want to deal with conflicts. So let's say if I would be allowed to implement a trait for any other crate, if the trait is implemented anywhere else, maybe in library 1 I implement a trait for one class, and in library 2 I implement the same trait for the same class, and then Rust will not know which of the implementations to actually use. So then it has this rule that you have to own one of the two. You cannot just implement willy-nilly. So for this reason, I cannot just implement my trait on the SPI. I have to create a brand new type that will actually be used to implement the trait that I actually want. So what I will say in here is that I create my own wrapper, and the wrapper is quite silly. It's a container of this SPI that HAL provides, and I'm saying the only thing that I need from this SPI is I need to write an unsigned integer, 8-bit unsigned integer, because if I can write one, I can write several, and these implementations allow you to write arrays. So this is great. And the next thing that I would like to do is I would like to implement a creation of such a thing, and then maybe some helper functions. So the first thing to do is new. When I do new, I just want to pass it in something, and it will take that something and autocomplete and return a structure. This is me for a convenience to not need to write down all this probably complex class that would go in here. And the next step that I would like to do is to flush it. So this means at some point in between the protocol, in between writing, I will need to have some sort of a delay. So if I go, I keep switching to the wrong window. If I go to the protocol in here, it will say that what happens between data refresh cycles. So how do I tell it that I want to go to the first LED or not? And the way to do that is wait for 50 milliseconds. So as long as I write 0, so I'm writing the value low for 50 milliseconds, I should be fine. So in this case, I'll create a loop. And I think I copied and pasted the comment from another project, depending on SPI frequency, but generally it's if you write 140 zeros, as long as your SPI is lower than 3.8 megahertz, you are waiting long enough. So this is my flush, and it should be good enough. The next implementation would be actually implementing LED writes. And LED writes is the same thing. I say as long as you provide me a write date, I can implement smart LED writes for SPI wrapper. Smart LED writes will require some types, which are easy enough. So one, this is where anyhow error helps me a lot, is because I can say type error is anyhow error and color is RGB8. And the only function that I am required to implement is a write implementation. The write implementation looks like this. So it says, as long as you give me an iterator, and this iterator is actually something that can be converted to a color. So you can see it's an iterator of items, and items can be into colors. I can return a result and either succeed or fail. So in this case, I would say this means that I can write one by one every value in the iterator. So I will do something like this. I know that I increase my data by 4, and the colors are red, green, and blue. Every red, green, and blue is 1 byte, so I have 3 bytes, and I expand them by 4, so I'll need to write 12 bytes in the end. So for every item in iterator, I will need to do the following. I know that my item can be converted to one color because it says into self of color. So I'll say this should be an RGB8 right now. My color is RGB8, and I would like to place my data, my converted data, into the buffer. And the way I do it is I know that the first 4 bytes correspond to green, then the next to red, the next to blue. The way I found this out is if I look at this description, it tells me the first bytes are for green, the next bytes are for red, and the final ones are for blue. Now that I have all the data, I will write it. Write in SPI returns its own SPI error. You can see it's SPI as write error and so on. I don't care what it is, so I just turn it to an anyhow error in case it fails. It never fails. And once I wrote all the items, I need to do the flush. So that wait of 150 or more milliseconds or microseconds. So self flush, and I am successful. This is it. So in theory, we have an SPI driver that can actually run. So let's test it out. The first thing to do is remember I need to implement memory allocation. I went into another video and I explained how to do that. In short, you allocate some sort of heap memory that is static allocated. In this case, I say I have 1 kilobyte of RAM, and you make sure that reasonably early in the program you initialize this unsafe memory. Great, so I have memory. Now what I need to do is connect to SPI and run my LED tests. So let's see how I can do that. So the first thing to do is figuring out what GPIOs I need. And I will show you a little bit of documentation of how I got these GPIOs and how I found that it's PA5 and PA6 and PA7 and so on. So let me save it, and I will do cargo doc open, and I will switch to the 4th window and hope that actually the documentation will open in this browser rather than in some other page. This took a while. In any case, so what I'm interested in SPI, and if I look at SPI, I know that I have several SPIs. I have SPI2, I have SPI1. I'm interested into the first one, and generally you are looking into the deeper implementations. What I expect is that peripheral access crate to be just constants. However, if I go into the SPI module, I expect this is the function that I want to use, and this describes everything that I need. It tells me the actual data type that I have to grab as the first parameter. It tells me what the pins are. It tells me about modes and RCC and so on. So now when I'm interested to see what can be a clock pin, what will be a master in slave out, and what can be a master out slave in port, I click on it and it will tell me. Like I could use PA5, I could use PB3 or PB13, and the same for all the others. I'm interested in master out slave in, because basically I want my microcontroller to output a pin. So the pin that I actually want to connect my LEDs to is this PA7, which is called MOSI. So I have these 3 pins, and I will also, at this point, I can create my actual SPI. And going through it, I got SPI1 from the peripheral access crate. I am giving it a clock, master in slave out and master out slave in. Polarity doesn't really matter because we're misusing these SPI interfaces. A clock, I've put it 2.4 megahertz, and the clock configuration, because this will set up how everything, how the clock's multipliers work, so I can reach speed close to this. I don't think I'll reach exactly 2.4 megahertz. I think I will reach more like around 3 megahertz, but it's close enough and it will work. And now let's see about LEDs. So I'll create my SPI, which is my SPI wrapper. And at this point, my SPI wrapper has the ability to change LED colors in theory. So let's try this out. So I will say that data is some sort of LEDs. And this time I won't copy paste anymore, but I will actually say, let's say we have 10 LEDs. And the way I would want to write it is I will say SPI write, and I want to write all the data. And I know it will not fail, so I just do unwrap. And before I do that, I would like to set some data. So let's say data of 0 will be red. So this is red is 255, green is 0, blue is 0, and into. And I will do red, green, blue. And maybe just a yellow, because why not? Notice that I said that these are 10 LEDs, 10 colors, but I only selected 3 colors. The rest should be 0 initialized, so I expect only the first 4 LEDs to light up, and the rest to not do anything. And I don't want this to loop that much, so let's say delay 1 second maybe. And let's see if this compiles. It doesn't, because I need to import a lot of stuff. So in this case, I'll go on top and I will import the mode, phase, and polarity. and the other bits that are needed. I don't think there are any others right now, at least not that I see in my example. So let's see, it doesn't know what SPI is, that is fair. So I can add a use for that. Oh, it already knows what it is, perfect. And any other errors? It doesn't have an allocation handler because I enabled the dynamic memory allocation. I need to provide what happens if I run out of memory. Let me copy and paste that. So if I run out of memory, I say I will print out of memory, and I will just loop forever and not do anything. It also tells me it's an experimental feature, so I have to explicitly enable that I am using an allocation handler. And let's see, are there still errors? It doesn't know what assembler is. So let me auto import it. And now cargo build. Cargo build release, because I want to make sure that it does fit into RAM, and let's say cargo run. And as you can see on the screen, the LEDs did light up. So if I go to the camera view, you can see that the LEDs are quite bright actually. So what I could do is right now, if I know that it works, I'll go in here and say this is maybe only 60 or 70. And let's see if I can change these fast. 70. So now if I run it, I hope that it will not be as bright. So let's see how that works. Yep, they dim down. So I have nice colors. Another thing that is in my demo program, and I will show it because I may as well copy and paste, is I can implement a way of generating a sort of color wheel. This is not my idea. It was taken from the example code from the smart LEDs. So the way it works is that it tries to do triangles of values. So imagine that I want to go from red to green and to blue. So what I will do is I will make red go from 0, 1 to probably bigger steps, because and eventually it goes to 55, and then I want to ramp it down, and I will make it 254, 253, and so on, and it will go up to 0, and then it will stay 0 for a while. At the same time, what I would like is that when red is at the top, so I'll start with green being 0, 0, 0, and so on until at this point, when the other one is 255, while the red ramps down, I would like green to start ramping up. So this will go 1, 2, 3, and so on. And at some point, it will get to 255 at the same time as red becomes 0. And somewhere in between, I will do the same thing with blue. So maybe blue I will keep at 0 up to here, up to fairly the end. And then at this point I will start increasing 1, 2, 3, and notice that at some point I will get to 255. And then when I start, I notice that I was 255 at the end of the cycle. So I'll make it here 254, 253, and so on. So you can see that each of these values go like kind of in a triangle shape. But they go at different paces, and this creates a very pretty color. So I have this wheel function that if it tells me a value from 0 to 255, it will go on a color wheel and it will give me a brand new color. So if I go in SPI write, I will say like for all the colors in the wheel, I will figure out an appropriate color on the wheel, and this is not generated by me. This is from an example, and I write all that data with a little bit of brightness adjustment. This is one of the things that LED library provides, is brightness is not as easy of just saying 1, 2, 3, and up to 255, because it's on a curve. So actually 254 and 255 are very close to each other, but not as close as, let's say, 70 and 71, even though in numbers they differ only 1 apart. So let's save this. I don't have num LEDs. This used to be a constant, so I will add it. I used 10, so might as well use it the same here. And it doesn't know what brightness is, but I can import it. Excellent. So now let's do cargo run release, and hopefully it will do some pretty colors. So you can see that they change reasonably nicely, and we have control over how many LEDs there are. So I'm looking how many I have in the screen. So let's do only 5, because I can see 6 are displayed on the screen. Another thing I will do, I will cut its power so to reset it so they don't keep the same color. So I resetted it, and now I'll cargo run release. And you should see that the 5 LEDs, they circle the colors reasonably nicely. So that was it. This is how you implement a NeoPixel driver for Cortex M0 reasonably from scratch, and you test that it works. Another interesting bit that we could do is I hooked up analyzer to see how the actual values run. So I'll run this and stop it. And here you can see how I misuse the SPI. So the clock is in 1 and the actual data is in 0. And you'll see several things. Number 1 is a clock is extremely accurate. So this is our clock, which we say, please make it 2.4 megahertz. Reality is it's 2.7 megahertz because you cannot get exact values. There's always multipliers and divisors, and they are powers of 2, I believe. So you cannot be always spot on. And the other bits that you see is, as I write these values, I've been writing values in multiples of 4. So for every byte, I would write 1, 2, 3, 4, and then another 4. And so I have red, green, and blue. So I have 12 bytes in total. And notice that in between these, I have a gap. And I have a gap both in the clock and in the data. And this gap is not allowed to exceed 50 microseconds, I believe. Right now it's 5 microseconds. This is why the LEDs work. So I don't have a perfect signal like the LEDs would want, but I have it clean enough, and it's close enough that it actually does move data around. And you can also see my final delay, where I try to say write zeros for a long time. Here it's visible. Like the clock thinks I'm sending zeros, but in reality the data line is just low. And this is what happens over the wire, and this is how you can debug various things, like me finding out that this separator between one byte and another, sometimes it was getting low, and this is why my colors were completely messed up. Would have been really, really hard to track without this kind of analyzer. That was it. I will post some code links into the video description, and I hope this is interesting or useful or both. Have a great day. Thank you.